All right, so next we're dealing with parametric equations. So if you guys recall, what we typically do with parametric equations is we take the x equation and we want to isolate t so that we can substitute it into the y equation. So I'm going to go ahead and start doing that. I'll subtract the 3 over. And then I will go ahead and multiply by 3. Now, if you look at this, we can actually already make our guess as to what we think this is, because there's only one set of parentheses that have x minus 3. So we're going to predict that it's D. But let's go ahead and continue the work anyway. So what I'm going to do is I'm going to leave that 3 when I multiply it to the other side. Instead of distributing it, I'm going to leave it in the front because in the answers, that's how it looks. So I'm going to say this is 3 times x minus 3 equals the square root of t. And then I'm going to go ahead and square both sides. So I have 3 times x minus 3 squared equals t. And when I square both of these things, I have to think about like writing this out twice, right? So I'd have 3 times x minus 3, 3 times x minus 3. And so 3 times 3 is 9. And then I have x minus 3 squared. Again, I'm not foiling all this stuff out because it doesn't look like that in the answer choice. All right, so now I can say y equals 4 times, this is my t value, squared minus 7. And if we think about squaring, again, exactly what we did here, 9 squared is 81. X minus 3 squared to the power of 2 would be 4. And I bet that 4 times 81 is 324. So you can kind of see, we already knew that's what the answer was, but that's what it should have been. All right, for the next one it says, what is another formula that represents the sequence? These are all explicit formulas. I know that because they don't have that sub n minus 1 piece to them. So what I can do is write down the first couple terms of this recursive sequence, and then I can go ahead and just check and make sure that works for these. So I have 3 as my first term. And then it says to get the next term, I have to do 2 times the term before it plus 3. So 2 times 3 is 6, plus 3 is 9. 2 times 9 is 18, plus 3 is 21. 2 times 21 is 42, plus 3 is 45. I probably don't need more terms than that. Okay, and then here is a nice kind of cheater way of finding this. So I'm just going to type all these in. 2 to the x minus 1. Nope. Minus 1. So there's my a. 2x to the third minus 3x squared plus 8x plus 3. 2 times x squared plus 1. 3x squared plus 8x minus 1. Okay, so I'm not going to graph these. I'm going to look at the table. So y1 is A, y2 is B, y3 is C. So what I'm looking for is one of these tables to match first term, second term, third term, fourth term. So this is my answer for A. First term, second term, third term, fourth term. So A is a contender. B, oh wait, that wasn't my first term. No, it was. Okay. B, first term, second term, third term. Nope, it's not B. C, first term, second term, third term. Nope, definitely not C. And then D, first term, second term. Nope, so it's definitely A. All right, for 15, first term is 25,000. What is the sum of the infinite sequence defined by the equation. So they gave us a recursive formula. They said to get the next term, you take the term before it and you multiply it by 0.8. So they're saying the first term is 25,000. The R value, what you're multiplying it by continuously, is 0.8. So the sum of an infinite sequence is the first term divided by 1 minus R. The first term divided by 1 minus R. Okay. What is the end behavior of this function? This is actually a logistic function right here. But the end behavior we can get just by graphing it and looking at the equation. So this means what is the y value when I look to the left? And this means what is the y value when I look to the right. Okay? So what I'm going to do is actually I'll just clear the whole calculator. There we go. So I'm going to type this in. 100 over 1 plus 5 times 0.75 to the x. And so it looks like on the left side we're trying to see if it goes to 0 or 1. And on the right side we're trying to see if it goes up forever or if it only goes up to 100. So what I'm going to do is I'm just going to make it go left to 100 and right to 100. And I'm going to maybe I'll leave it as -10 and then 200. And you'll see kind of why I'm doing this in a second. Okay, so this is really clear, I think. Does the graph go up forever? Nope. It levels off halfway in the picture. So my picture went up to 200, so that means it levels off at 100. So on the right side, the y-coordinate, as the x value goes to the right forever, the y-coordinate on the right side is definitely 100, so that narrows it down between B and D. So now we need to know on the left side, does it go to 0 or does it go to 1? And so it's kind of hard to see. I'm going to change my window and make this go to just 10. See if that helps. That did not help. Okay, so here's the next best thing. I'm going to hit trace. I'm at an x value of 0. I'm just going to follow this to the left. Oh, and look at that. So what's happening, if you guys recall, anytime we have that e, it means that the value is very close to 0. So what happened here is the further left we go, and we don't even have to go left very far. At an x value of 0, we have a y value of 16, then 9.7, then 5, then 3. So here it's like, oh, could it be going to 1? Nope. Nope. It's getting smaller and smaller. And then what's happening is you'll notice these decimals are getting closer to 0. And then this is just saying take the decimal, move it 4 places to the left. It's just getting smaller and smaller as that decimal. So that means that on the left side it's going to 0. So the answer is B. So even if we didn't know what a logistic function was, it didn't matter. We could graph it to find the end behavior, what it was doing on the far left side of the graph, what it was doing on the far right side of the graph.